Hello and welcome to a hopefully interesting and hopefully not too morbid video on the death rate in Canada. So in a previous video, we acquired a dataset that shows life expectancy at different years and different ages in Canada. And we used it to make these interesting colorful surface plots here that show how the life expectancy gradually changes as you get older and older and older. And as you can see here, the life expectancy generally decreases over time, which seems to indicate that every single year there's a certain probability of surviving until the next year. So is there a way we can actually use the life expectancy data to compute the survival probability? I think actually there might be. So let me begin by showing you a quick model I constructed here to understand this idea. So let's suppose we're at year number 5 here and we have a life expectancy of 0. Well, that means we have a 0% chance of surviving to the next year. But then for year number 4, let's suppose there's a 20% chance of surviving until year number 5. Well, in that case, our life expectancy must be 0.2 multiplied by 1 year, so 0.2 years. For the year before that, year number 3, if there's a 50% chance of surviving until year number 4, then our life expectancy must be at least 0.5 years. But we also have to add 0.5 times the 0.2 years we have once we reach the age of 4 here. Furthermore, if we take a look at year number 2, with a 70% chance of surviving until year number 3, the life expectancy must be at least 0.7 times 1 year, but also 0.7 plus times 0.6, getting up to 1.12 and so on and so forth. So in general, we can write that the life expectancy at the current year is equal to the probability of surviving until the next year multiplied by 1 plus the life expectancy at the next year. And rearranging this, we find that the survival probability is just the current life expectancy divided by 1 plus the expectancy of the next year. So since we have the life expectancy, we should be able to compute this survival probability for every single year. So let's take a look at the data frame we imported. Basically here for the year 2010, if you're 0 years old, you have a life expectancy of 81.4 years. If you're 1 year old, you have a life expectancy of 80.8 years. So right now we want to take the sort of first entry in this data frame and divide it by 1 plus the next one. We want to do that for every single column, every single row. So to do that, we're going to make a copy of the data frame, but shifted backwards by 1. So you can see this 80.8 value we have here, that's been shifted into the primary position from the second position right here. Then we can simply compute the survival probability as the initial data frame divided by 1 plus the shifted 1, and then we can fill out the not a number value that occurs in the very end, but just with zeros, which kind of assumes that once you hit the maximum age, you have a 100% chance of dying, which of course isn't really completely accurate, but it's just for the to make the data a bit more well behaved here. And then the death rate, of course, must simply be 1 minus the survival rate, obviously. So now let's just plot the data for 2017 to see how it looks. We can see that the survival rate is very high generally, and then it decreases as you get older, and the death rate is very low in the beginning and then increases as you get older here. And plotting the death rate on a log scale is maybe a bit more informative. We can see that there actually is a certain amount of infant mortality right here. Now, I'm not entirely certain that the data we have available in the model I'm applying here is really very useful for the, let's say, the first year of life, since a lot of, let's say, biological changes that happen to an infant during that first year happen sort of on a month-to-month time scale. So the single year we're looking at here, and the data simply averages that out. So I'm not entirely certain that value is really maybe too accurate. But I think for older ages, when changes in your health and your body is a bit more gradual, this should be a fairly descriptive model. We can see that generally in childhood, the death rates are quite low, around 1 part in 10,000 almost. And then it slowly increases as you get older. And then this spike we see in the end, that's because I set the death rate to 100% when you hit the maximum age here, which of course isn't completely accurate. So to get a picture of how this looks for all the different years we have on record, we can create another color plot here. So we're going to plot ages and years as before, and we're going to set the height and therefore the color to simply be the death rate. So if you do that, we get a chart like this. So we can see that we have a slight positive shading here, so that's the infant mortality, and then it decreases to a very small value here during childhood, and then it gradually increases towards 100% here in the end. Notice the white area right here, so that corresponds to data entries where the survival probability is essentially 100% from 1 year to the next, which means the death rate is 0, which means once you compute the log of the death rate, you don't really get a sensible number out, so it just becomes white right here. And the fact that these sort of white blotches appear sort of for later years, like 2015, means that generally the death rate has decreased over time compared to 1985, which I guess is the good news. So anyway, I hope you found that interesting. Sorry, it's a bit of a morbid topic, but I thought it was an interesting way to explore the data that we acquired here. So check out the source code in the description, and I'll see you in the next video. Bye-bye.